Right, welcome everybody to the first look at your set of questions on measurements and uncertainties and stuff like that. Mostly though, it seems to be things about forces that you're having issues with. So let's try and get into this. Right, I'm going to look at question 2 first, which is about impulse, change of momentum, and rockets. Now, I'll just flick this to the one I've got where I've been writing in answers for you. Right, you had a first one which was about the relationship between impulse and change of momentum, and then show how using that you can show that the units, newtons, force units, are actually the same as kilograms meters per second squared. Now, the way I've done this is I've just said, right, okay, no worries. If we look at, first of all, the equation that relates to all of this, impulse. Right, impulse is force multiplied by time. So you've got that. And if you remember, that causes a change of momentum. And your change of momentum is, now I've written it as delta mv, so change of mass times velocity. Now, all I then did was said, right, fine. If I've got to show the units are equivalent, or got to show equivalence of units, I'll just note down the units of those two. So, force is in newtons, time is in seconds, momentum is kilograms and then meters per second, like that, because it's mass times velocity. And so, what I can do is then, right, okay, I'll rearrange it in terms of the units. So, newtons would be that divided by seconds. And you've got seconds to the minus 1 divided by seconds, which makes seconds to the minus 2. And there I am merrily writing it wrong, writing it incorrectly. So kilograms meters per second squared, which is what we were asked to do. So when I'm doing that sort of thing, I just stick the units in as my way of and rearrange them as if they were numbers or items in a formula. Right, now, so that's force multiplied by time gives you a change of momentum. The larger the force, the longer the time, the bigger the momentum change. And that also, if you recall, that also tells you that you can use Newton seconds as a momentum unit as well. Quite a handy thing. If you can't be bothered to keep writing kilogram meters per second, you can just write Newton seconds. Right, got your little picture of a rocket here to help with this. Rockets use liquid propellant. That means rockets that actually mix two fuels together, or they mix fuel and an oxidant. Those react, produce huge amounts of high temperature waste gases out the back, and that makes the rocket move in one direction, as opposed to a solid rocket where you just light up a solid material. That's like your typical fireworks. This is also, of course, the way that those water rockets work, except that there's no burning goes on, it's just the pressure blasting the water out the back. So they said, explain how ejecting, that means pushing out, waste gases in one direction. Here are the waste gases coming out of the rocket, boom, that way. How the ejection of the waste gases in one direction makes the rocket move in the opposite direction. So you're getting opposition of things there, and inevitably this leads you to start thinking about Newton's laws and things like that. So what I've said was, right, do it in terms of change of momentum, which is what this is all about, and conservation of momentum. Right, if you're chucking all this gas out the back at very high velocity, and I've called it V1, the velocity of the gas, and if that gas has got a mass of M1 and a velocity of V1, and they said, right, okay, coming out per second, if you like, then momentum has got to be conserved. Before the rocket was switching its motor on, there was no, it was going at a constant momentum. So you're going to have to conserve momentum. So the momentum change one way is going to have to be the same as the momentum change the other way. So I've got that here. I said if your rocket's mass is M2 and V2, then the overall change in momentum has got to be 0. So I've said, right, M1, V1, the momentum change caused by the fuel coming out, by the exhaust gases coming out the back. summed up with the change of momentum of the rocket will be 0. So that means that one and that one are equivalent, but they're in opposite directions. So you've got V1 and V2. This is one of the things they particularly wanted you to mention, was that these are vectors and they've got to be in opposite directions. The momentum changes must be equal and opposite. Another thing to say there. So you've got momentum one, you've got velocity one direction causing velocity the other direction. They're in opposite directions, and so that is causing your rocket to move forwards. So there I have, okay, rocket mass V2, right, M1, so it must be, so you've got to produce a velocity in the opposite direction. Right, if you were doing this in real detail and being a proper rocket scientist, of course you could point out that because it's chucking fuel at the back, the velocity of the as the velocity of the rocket is changing, it's also losing mass. So it'll actually accelerate faster the longer you leave the rocket motor on, because you're losing some of its mass as well. Right, there's an alternative way of doing this. You can just talk about forces instead. There's a momentum change for the fuel, and that produces a force. Yeah, so F1 multiplied by T for the time the motor's running, and then so you get this momentum change for the fuel, produces a force. Newton's second law, that is, that's F equals ma, except I've got V over T instead of A. So that force produces an equal and opposite force, Newton's third law. So Newton's second law there, Newton's third law there, and so that force makes the rocket move, if you like, from rest in the opposite direction. Bit weird that they've actually just said, yeah, it makes the rocket move. I would have thought make it accelerate would be a better way of saying it, but that's what they've got. So that's nice, straightforward, simple stuff. Move on to part C here, and they're actually giving you numbers to use. It produces that many kilograms of waste gases in a second. It's got a speed of 2.4 kilometers per second relative to the rocket. When you do about Einstein, you find it doesn't matter whether things are standing still or not. It's the relative velocity that matters. So that means we've got to show our calculations that the average thrust on the rocket is about 40 meganewtons. Okay, so I've done this, and what I've said is, right, here we go then. First of all, I've said, right, well, let's just be consistent with our units. Instead of putting kilometers per second, I'll do meters per second. So instead of 2.4 times 10 to the third, and the meganewtons is 40 times 10 to the sixth, just in case that's going to matter. Right, and you can use again Newton's first law. Force is rate of change of momentum. I have got a change of mass here of, well, I've got an amount of mass here, 1.5 times 10 to the 4 in a second, and I have got a velocity that mass has got, that much, and then dividing by the time, I'm doing it for 1 second for both of those. So I multiply those two together, I get 3.6 times 10 to the second, or 36 meganewtons, and it's about 40 meganewtons. So that's done. This bit about the reason they said average thrust doesn't need to worry you. It's just that you are, it is sort of giving you an average thrust. Yeah, in fact that should be fine. It should be the same amount of mass coming out per second, and so the gas being ejected with 2.4 kilometers per second relative to the rocket. Yeah, those will both stay the same, and so that gives you that answer. So 36 meganewtons. And we've done it because we were expected to get about 40. When you do this, remember, quote your significant figures. I've actually gone through with just 2 here. You don't have to round anything up, because that is 3.6. Yeah, it's 3.6000. But I've stuck with the 2 sig figs they've got here, and I've got my 36 meganewtons and comparing to the 40. So I haven't had to go to any further decimal places or anything. Right, that's nice enough. I will do a part 2 on this, by the way. Don't worry about having to do the whole thing in one go, because it gets a bit dull. Right, jet engines. This is what they've had this for a long time with jet engines. It's ever so clever. You end up with a massively heavy aircraft after it's landed, and you don't want to have to just use the drag of the flaps and the air brakes, and most especially the wheel brakes and the tyres to slow the thing down. That's going to be really bad. So what they use instead is they have something called reverse thrust, and it's the same rocket engine, but they put these sort of big clamshell type things can close over the back of the engine, and that directs the exhaust gases, instead of backwards, it shoves them out sort of sideways and up here a bit. So that's a way of slowing down the aircraft, is by reversing its thrust, making the thrust go forwards rather than backwards. You'll see some other ones now, they'll actually have kind of doors that open up in the side here instead. Does the same job. They'll open up the sides, and so you'll actually end up with doors that open up here, and the exhaust gases come rushing out from here. That's another way they do it. They even do this on turboprops as well, like C-130s. You do it with the angle of the propellers. So you have the propellers like this, the blades that come out, and they swivel them, change the angle which they're pointing at, so that even though the blades are still turning the same way, they produce a force in the opposite direction. So ever so clever the way they do that. So the propeller blades, they turn, that one will turn that way, that one will turn that way, and so they'll actually end up reversing the direction. They'll reverse the thrust instead of pushing it along. Instead of pushing it along, they'll push it backwards. Now, in this first instance, this jet engine is working normally. The aircraft is going this way. Air's coming in from the front and going out of the back of the engine. Right, I've done that because that's part B. So heated up, the air expands, it comes out big at a much higher speed due to you burning fuel. What happens to the momentum of the air? It goes in slow, it comes out faster, its momentum increases. That wasn't hard, was it? Then, using the appropriate laws of motion, why does the air exert a force on the engine in the forward direction? Okay, well, what you can say is, you can expand upon what was said here, but you have got for the air, its momentum increase backwards, and therefore for the plane you have momentum increase forwards, right? And so you are again doing conservation of momentum. It's the same arguments that we had for the rocket, except that you just have to think instead that the air is increasing its velocity, so its momentum is increasing. Okay, and so that has to be balanced by an increase in momentum for the aircraft in the opposite direction. So you do it conservation momentum, or you can do third law as well. Force in one direction equal an opposite force in the opposite direction. It's the same arguments that I was using back here for why the rocket produces the thrust backwards. Gas is ejected at a velocity v1. Well, in the case of this, it's ejected at a higher velocity. Sorry. So the air from the jet is sent out at a higher velocity. So the momentum has been increased going backwards. So the aircraft has an increase in momentum forwards. Right. Next bit of this. Right. Calculate the force that the engine exerts on the aircraft. Oh, go on. Calculate the force that the air exerts on the engine. Yep. Okay. Attached to the aircraft. Again, same thing. An amount of mass, and the mass of the air increases by 570 meters per second as it passes through the engine. And here again, 1 second. So it's the same formula. Change of momentum divided by time. It was that much mass of air. had its momentum increased by 507, sorry, had its velocity increased by 570. Put the two together, you get 119,700. All of these numbers are 2 sig figs, so I've taken that down to 2 significant figures, and I've got 120,000 newtons. So again, I've used the same arguments as the previous question. Now, here we go with the deflector plates, they're calling them, for the aircraft being decelerated once it's got down onto the runway, and they cause the air leaving the engine to be deflected at an angle to the direction of the aircraft. So they're not coming out straight backwards, it's coming out at an angle, but it's no longer going the same direction as it was when it came in. Right, and so here we have, right, it says the speed it's leaving, the speed, notice the use of that word speed, not velocity. It's the same speed coming out at B as, yeah, the speed, so it doesn't actually slow down going from there to there, it's just deflecting off, so it's still going at the same velocity when it's come out there. But they're asking you then, why does the momentum change? It's the standard stuff. The direction of the air velocity changes, and as momentum is mass times velocity, there is a change of momentum. So I think one of the things I maybe need to say a little bit more clearly here, I've said that the momentum is also a vector, so maybe just to make it a bit clearer, point out that the velocity is a vector. The direction of the air velocity changes. Momentum is mass times velocity, so there's a change in the momentum of the air. And yeah, and they're asking about the force. They're just asking you, why does the momentum change? Because the velocity changes. Velocity is vector, direction changes velocity, so, and momentum is mass times velocity, so there's a change in momentum as well. Good stuff. Incidentally, they have occasionally been complete losses of aircraft when these things come open while the aircraft is flying. Then suddenly you've got one engine trying to make, if it's got two engines, you've got one engine trying to make it go forwards, one making it go backwards, and the aircraft tries to turn left or turn right and then drops out of the sky. Usually these are set up with all kinds of electrical and mechanical and whatever you can interlocks, so that they will only open when the undercarriage is on the ground, when the undercarriage is being pushed upwards by the ground. These will deploy, so they won't deploy when the aircraft is still flying. They're supposed to only be capable of deploying when it's rolling along the runway. So they actually have little systems to stop them coming open when the aircraft is airborne. Right, right. Last couple of little bits here, I think. Yes, last couple of little bits. Total horizontal decelerating force is 180 kilonewtons. Right. Calculate the deceleration. So, standard stuff, GCSE. Right, force is mass multiplied by acceleration. Acceleration is force over mass. There is your force, 190 kilonewtons. They've told you that the mass of the aircraft is that much. Put the two together. Divide the force by the mass. You get 2.714 meters per second squared. Again, drop it down to 2 sig figs, call it 2.7 meters per second. Right, and then in the next one, bit trickier, but again it's only GCSE stuff. It lands on the runway at that speed, and they want you to find out how long it can go until it comes to rest, meaning v equals 0, and 68 meters per second is your initial velocity. So u equals 68 meters per second. You've been told the acceleration there. Now, oh sorry, you've calculated your acceleration, right? And they said calculate the deceleration. So what I've done is I've reused that number, but I said, right, well it's a deceleration, so I'm going to give it a minus number. I'm going to call my u 68, I'm going to call my v 0, my acceleration minus 2.7. Find the appropriate SUVAT formula. You've got one here which doesn't have time in it because we don't know anything about that. V squared is u squared plus 2as. v squared is 0, u squared is 68 squared, and then minus, and if you want to be pedantic about it, put brackets around that, minus 2 multiplied by the acceleration 2.7 multiplied by s, and the minus there has come from this being a minus acceleration. And then if I rearrange this, I can actually then get that s is, bringing my s over here, s is minus 68 squared divided by minus 5.4. Note it's 68 squared as a minus number, not minus 68 squared, because then that would be that would end up as a plus. So you end up with minus and minus cancel out. The whole thing comes out as a positive 856.3. I've done 2 sig figs again, rounded it to 860 meters. First time I did this, I cocked up. I forgot to put 5.4. I did it 5.4, and I got a stopping distance of 86 meters. And I did think that's rather short. That's more like it. I mean, runways are, you know, can be 2 or 3 kilometers long in some cases. They're long for airliners. They're very long. The only reason they can land aircraft on aircraft carriers is because they've got a big piece of wire that the aircraft hooks to, and that slows it down. Right. Okay. So, right. Why don't you get the same decelerating force from these deflector plates all the time? Right? Why is it that the decelerating force isn't the same all the while? Well, if you think about it, it's the force is caused by the momentum change, and in this case you've got air coming in the front and then being sent backwards. So you've got, say, when it first hits the ground, you've got high velocity here and then a high velocity backwards. So you've got a big change. When the thing has landed and already started slowing down, then you've got the velocity of the air coming in is slower, and so even though it's been reversed, you haven't got as big a momentum change. I've just written it there as the incoming velocity magnitude decreases as the aircraft slows, so less momentum change, and I should really have said because less velocity change. Alright. There is an alternative way, and so because there's less velocity, because there's less momentum change, there's less force. Alright, that's the one they wanted there. So the highlighted bits of that are incoming velocity varies, it decreases, and there's less momentum change because there's less velocity change, and therefore there's less force. You can also argue, you can get the marks for this by saying that the mass of air entering the engine decreases, and that also causes less momentum change. The aircraft is going slower and there's less mass of air going in each second, so you've got that as well as an alternative. Right, now that's the first 2 questions. The next 2 are these horrible things about sort of practical skills, though they're weird questions, but I'm going to stop that here and then do a second short video for the other one. See you soon.